Okay, so I'm recording now. This again, maybe 15, 20 minutes or so. This will take me. This section will kind of cover some of the information that was in your lab this week. Now, we didn't have a lab on campus, so this lab you can submit, this weekend. I mentioned in the course that it was due Thursday. If you guys need more time, you can take the weekend, no problem. So let's look at this section now. There's a lot of outcomes here, but it's pretty straightforward. We're basically going to look at electron dot formulas for covalent compounds and also look at this idea of the Vesper theory, valence shell electron pair repulsion. We'll talk about that in tomorrow's class. So for today, I just want to talk about covalent bonding in electron or Lewis dot diagrams. So covalent bonds are different than ionic bonds. Covalent bonds are only between non-metals. If you compare that to ionic is a metal and a non-metal. They have a transfer of electrons. Covalent bonds are not between metals and nonmetals. They are between nonmetals only. So things that are on the right of the periodic table to the right of the staircase. So things like carbon, oxygen, fluorine, chlorine, sulfur, nitrogen, these would be involved in what's called covalent bonding. Covalent, meaning they kind of share their valent or valence electrons. So we learned a little earlier in this chapter that the octet rule is what makes ions or elements stable. Elements or ions, atoms, I guess I could say, they try to have a full octet, meaning they want to have 8 electrons outside them. There is an exception with elements like hydrogen, which I'll talk about in a minute, but most of our elements need a full octet or shell of 8 electrons. So there's a question I have here. How does F2, the molecule fluorine, become stable? Well, the atom fluorine has 7 electrons. It's in group 7. So it or group 17, I guess you could say. So it has 7 electrons. It's missing 1. So what happens is when fluorine gets together, 2 fluorine atoms, they decide to share their electrons, their single electrons. Oops, sorry. So nonmetals want to gain electrons and they share between them. The smallest unit of a covalent compound we call a molecule, whereas ionic compounds we would call a formula unit. Sorry about my pen there. Well, for covalent compounds, not ionic, for covalent, we just call them molecules. And I mean, the classic water or classic molecule you can think about is water. So I'll get to this water in a second, but let's look at some properties that covalent compounds have. Ionic compounds are typically solids, okay? They're crystalline compounds or crystalline chemicals. So things like salt, table salt, NaCl is a white crystal, a white solid. Covalent compounds have a little bit more of a range. They can be solids, liquids, or gases. So like water would be a liquid. Something like methane would be a gas. And then something like, I don't know, sulfur would typically be a solid at room temperature. Covalent compounds typically have lower melting and boiling points compared to ionic. Like again, you can look at water. Water would melt at 0 degrees Celsius, whereas something like table salt, NaCl, melts at 800-900 degrees Celsius. So covalent compounds are typically lower on the melting and boiling point scale. They're also very poor conductors of electricity. Because they're sharing electrons, the electrons can't move like in an ionic compound. So in an ionic compound, the electrons are kind of moving and can be transferred. That's what electricity is. But in covalent compounds, they need to stay where they are. So there are no ions to move. Again, ionic compounds have ions. And if you don't have ions, it's very, very, very difficult for the electrons to move. Okay. Oh, and one thing I'll mention, by the way, is none of this is on your test on Monday. The test on Monday stops at the section before this. All right, so all I want to do for the rest of the class today, we're going to practice drawing a bunch of electron dot formulas. I'll show you the steps here, and then we'll practice a few. So here are your steps for drawing electron dot formulas for ionic compounds. Step number 1, draw each individual element of your molecule. So in this case, I'm picking water, one of the most classic molecules. And even before I draw this molecule, guys, just look, like if this was a puzzle, it fits together perfectly. Water has 2 hydrogens and 1 oxygen. The oxygen has 6 electrons because it's in group 16. Sorry. And water only has, hydrogen only has 1. It's in group 1. So when you look at this compound, you can kind of see where the hydrogens would go. They would go to complete the octet for oxygen. So step 2 says find the central atom. The central atom is the atom that you kind of put down first. It's the one that is in the middle of the compound. This is the atom that has the most bonding electrons. So just to review, what are bonding electrons? Single electrons we would call bonding electrons. Electrons that are paired up, as in a group of 2, we call lone pairs. They are not involved in bonding. So if I look at this chemical, or I guess I look at the atoms involved, hydrogens can only form 1 bond, whereas the oxygen can form 2. That means the oxygen is the central atom. It's the one we put down first, and all the other atoms are connected to it. So step 3, all elements must be stable with 8 electrons. Now there is an exception to this rule, and hydrogen and helium fit this exception perfectly. Hydrogen is just too small to have 8 electrons, same as helium. Hydrogen only has 1 proton. So hydrogen and helium are so small, they only need 2 electrons. Everything else will basically follow our rule. Certainly in covalent bonding, things like nitrogen, oxygen, carbon, they will need to have 8 electrons. Again, hydrogen is just too small to hold on to 8. It only needs 2. That would be its first energy level, 1s2. Okay. So step 3 is share all of the bonding electrons. Any single electrons will be shared. And once you've shared them, meaning you put them together, you just draw a tidy molecule at the end. So this is the Lewis structure or electron dot structure for water, H2O. This idea of the structure is really important for understanding the properties of these chemicals. I have 2 lone pairs and I have 2 bonds. And we're going to look at this in tomorrow's class to help us predict properties of these chemicals. So let's practice this. I have 2 examples here, and then I'm going to show you some double bonds, and that's it for today. So maybe I'll just do one of these and give you guys a minute to practice the other. So I'll start up here with NH3. So step one is to draw the atoms and their electron dot diagrams, I'll say. So hydrogen is really easy. It's just H with one dot above it. Nitrogen, it's in group 5 or 15. So nitrogen would have 5, not 15, 5 dots around it. So 1, 2, 3, 4. Sorry about that. 5. Now note that I have 3 hydrogens. I'm not going to draw all 3 of them, but like you can kind of see in your head how this is going to be put together. The nitrogen has 3 electrons that can be bonded. The hydrogen, well, there's 3 of them. So this is a pretty straightforward molecule. I'm going to draw my nitrogen. This will be my central atom. Okay, so there's nitrogen. And everywhere there's a single bond, I will put a hydrogen. So hydrogen, 1, 2, 3. There we go. That is NH3 ammonia, that we call NH3 ammonia. There you go. That's it. You'll notice that the nitrogen now has 8 electrons around it, and the hydrogens all are happy with the 2. So I'm going to mute myself and just pause the recording for 2 minutes and give you guys a chance to try CH4. So I'll be back in 2 minutes to see how you guys are doing. Okay, let's look at this compound. This is methane, by the way. If you've never heard of methane, this is the #1 country in the world where you should know about methane. Methane is a natural gas that we get from refining petroleum. And Qatar is actually the #1, or at least it was when I looked this up a few years ago, the #1 exporter of LNG, liquefied natural gas, in the world. So more specifically, methane used as a fuel source around the world, most of it actually comes from this very small country. So it's kind of impressive. I think the number I read before was almost 70% or more of the LNG, liquefied natural gas, comes from this country. Pretty cool. So this is methane. And to draw this, I would start with carbon. It's in group 14 or 4A, meaning it has 4 bonds. And then around that, I would have 4 hydrogens. Now, again, guys, think of this like a puzzle. If you had 4 single electrons on carbon and 4 hydrogens, it's like a perfect match, right? You would draw carbon in the middle. Sorry. This pen, one of my coworkers told me I might be able to fix this pen problem, but I haven't been able to yet. All right, so there's carbon. And now I'm just going to stick onto it 4 hydrogens. So each hydrogen has 1 electron. That's perfect. It gets matched up with each single electron on the methane. And there we go. That's methane. It's a carbon bonded to 4 hydrogens. Pretty cool, pretty easy. All right, sorry, I'll leave that out for a minute. Now, before I finish, there is obviously one topic I want to cover about double bonds, because I've showed you right now some pretty easy ones, but they can be a little bit more complicated. So if you'll let me do 2 slides, I want to do this one, and then this one, I'll be finished for today. So electron dot diagrams can be a little more complicated because sometimes elements will share more than 1 pair of electrons, and we would call these double or triple bonds. So in the realm of, we'll say, organic chemistry, you can have single bonds, which we see a lot, but things can also pair up to form a double or triple bond. So I have oxygen down here for an example that's showing a double bond, and nitrogen, for example, showing a triple bond. We're going to practice these now. So let me show you two more. I'm going to leave this one for you guys to try. This is a hard one, but I just want to do these two. And again, this one maybe I'll do in tomorrow when I start the class up. We'll do this one. But for right now, let's just look at these two. Okay, so here's now for this one, I am going to draw every molecule because this, or every atom, this will give us a good picture of what it will look like. And even this one down here. So carbon. Carbon has 4 valence electrons. And then I'm going to surround that with oxygen, which has 6. Again, carbon is in group 14, so it would have 4. Oxygen is in group 6. Now, if I draw it like this, and guys, I have a little bit of experience with this, so, I've drawn 100, maybe 1,000 of these in my life. I'm kind of cheating, meaning I'm organizing it the way it will finally look. But think about it. Carbon has 4 single electrons. It has the most single electrons, so it goes in the middle. And I need to attach to that 2 oxygens, which also have 2 single electrons. So think about like what this will look like. The single electrons on the oxygens, I have 4 of them, 4 total. They will go to the single bonds on the carbon. I think there's a question in your lab this week. I haven't gotten anybody's lab yet, and you can take your time with the lab, no rush. But there's a question in the lab, like what happens if you draw a molecule and there's still single electrons? That means there's a mistake. These molecules are designed to perfection by nature, meaning there's not going to be any single electrons left over. If there was, it wouldn't be a molecule. It wouldn't work. So when I ask you on later, this is not on your test, obviously, but maybe on your final exam or in the lab this week, I ask you to draw a molecule. I have selected that molecule because it's a real molecule and it should fit perfectly. Again, what I'm trying to say is I'm creating like this puzzle for you, but the puzzle will be perfect. It has to be because it exists. CO2, I mean, you're all breathing it out right now. So CO2, I would have double bonds. Okay, it doesn't really matter where you put your lone pairs on the oxygen for right now. It will eventually matter because we're going to learn about something called valence shell electron pair repulsion. Sounds really complicated, but it's not. But there's CO2. I have double bonds. So what CO2 would actually look like would be like this with double bonds and lone pairs. I think actually one of the questions in your lab is you have to draw CO2. So there it is. Okay, let's look at the other one, and that'll be it for today. HCN. So I'm going to draw each of these molecules. Let's go with green. Green's my favorite color, but I never use it for my slides. Green or brown, they're my favorites, my fave colors. Okay, so think of this like a puzzle. Like, don't think of this like chemistry class. Think of this like a puzzle where you're trying to bond everything together to be one happy molecule. For something to be a happy molecule, it needs 8 electrons. Hydrogen is our exception. It only needs 2. But I mean, this is like a perfect match. My carbon is going to be my central atom. The carbon has 4 electrons, so 4 bonding electrons. So this is my central atom. Now around it, I have hydrogen that has 1 electron and nitrogen, which has 3. So again, think of I mean, this is like, the how beautiful chemistry can be at times. This is like the perfect match. I got carbon that needs 4 electrons, but I also have a hydrogen and a nitrogen that have 4 electrons to share. It's like the perfect match. So I'll keep the C in the middle and we'll do a triple bond. Now, when you do a triple bond, you can draw it like this as well. I tend to do it this way that you can see there. I do 6 electrons. That's my triple bond side by side. I don't really care as long as you don't like just throw the dots in randomly. It doesn't matter how you show me the dots, but this is typically how I would write it. And then hydrogen over here. One thing I should mention too, I probably should have mentioned this a while ago. Think about the law of conservation of energy or law of conservation of matter. I can't add any electrons here. I can't add anything. Like what I have in the initial problem is all I can work with. So if I look at the initial problem, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons total. And here I must also have 10 electrons total. So I won't mess this up, but I'm just going to count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 electrons. It's perfect. I had 10 electrons on the left. I had 10 electrons on the right. So I didn't break any rules. Okay. So guys, that's it for today. I think I only, how many students do I even have right now? Not many. I still only have 7 of you. Oops, sorry. So I'll leave it there for today. What I would like for you guys to do is if you're bored tomorrow, you're waiting for class or you got nothing to do tonight. I know you guys have labs and assignments and midterms, and I know you're very busy. But if you're bored, you could try this example here, Fe. It's not that hard, but it would be a good challenge for you guys because there's 2 central atoms in this case. The carbons would go in the middle, and I won't say anything else about that. So other than that, I'm done. I'm going to hit stop record, and if you guys have any questions, let me know in the chat.